lambda calculus. So this theory is going well so far, it seems, at least on my side. We've been doing this, selecting the first of the two. And one interesting thing popped up now. Interesting thing popped up. The thing about lazy evaluation, or eager evaluation, or as it said, call by need and call by value. So I think a couple of times I did get a different solutions, and I was talking about that I'm not sure. When do you expand? When do you expand or like substitute the function definition for the function name? So I think in call by need, right? Well, I think in call by need, you basically do the computation when you need it. In call by value, you evaluate the arguments, and then you kind of do what you need. It's almost like doing something in advance. But the thing is, let's say you have a choice between two things, and you will choose the first thing, and the second thing does not compute, right? Or you kind of does not compute in the sense that, let's say you divide it by 0. In call by value, this will not work, because the function will evaluate both branches. And if there is one branch where you have divide by 0, the whole thing won't work. But in call by need, it will work if you need the branch, if you need the first branch, right? So, and then I watched, this is very fascinating, this thing with call by need and call by value. And it seems to be kind of like two camps in functional programming languages. Interesting. So the call by need, I guess the champion would be ML, call by value, and call by need, Haskell. But it's just interesting, and when I look at the research, they have a totally different way of approaching this kind of, it's like a different language of describing computation. So the call by value, I guess it's more operational, and call by need is more denotational. But then Simon Peyton-Jones said in one of his talks in Lazy by Class, he said that the future Haskell will be pure. So he's not like so emphasizing call by need. Although in other talks, yeah, he was saying when he was younger, right, the call by need was the way to the, was the way. And call by value is even in some terms was described as the deal with the devil, right? It's interesting. But it's, yeah, I'm now going into this. I really don't have the capacity, or I don't know much about these things. So I'll just return to this. But actually, why did this pop? Because I was substituting some function names for their definitions before I would actually apply them. So I would substitute them. Like, I remember I would like substitute here the identity, and then I would do the change here. Instead of, for example, substituting the identity here for the first and the first, I would, well, these are just small functions, right? But let's say they were bigger, and then I would substitute. It's possible I might have gotten a different result. Yeah. Maybe this is not clear what I'm saying. Yeah, still not clear. So I'll just get back to the select second. We were doing the select first identity, select second identity, first, second identity. Yeah, so the select first or the select second is actually the K combinator. The combinator that takes the first thing or the second thing from two things. Consider the function. And body second first. Select first, that's what we did. Select first, selecting the second. Okay, selecting the second of the two arguments. Consider the function. Select second, first, second. This function has bound variable first. And body second. So again, this whole thing is a function, and the head has a bound variable first, and the function body itself, right, has a second. So again, even though there is a dot here, right, so this is also another function that in the head has the second and in the body has a second. But at the same time, when we zoom out, it's another function, right, with the head first and the body second. So which is another version of the identity function. So yes, it's useful to practice this like this. So we're doing actually alpha conversion, you could say, on the fly. So lambda second is same as lambda bb or lambda blup, right? The meaning is the same. Interesting. First, second. It's same as identity. Yeah, which is another version of the identity function. When applied to an argument, select second returns a new function, which then applied to another argument returns the other argument. Okay, now I understand what was meant here. One of the things why I'm doing this like this so slow, it's because you need practice. My CPU is at 99 again. Oh yeah. Will it go down? It's going down. Good. But my memory is pretty high. Okay. So it's important to practice, you know. At least that helps me. And it's fun. When applied to an argument, select second returns a new function, which then applied to another argument returns the other argument. Select second identity, apply first, second identity. Identity substitutes. Well, identity substitutes the first. Yes, that's clearer now. Look at this. So the identity. Will this thing work? Oh, it's like this. Identity goes inside instead of the first, and we have the second, and then we just drop identity in the first. And then we go with the apply. And we have second apply, and this is basically like the identity. We just, gives us back what we provide, which is apply. And we do not need to evaluate apply. Well, maybe that's the wrong word. We do not need to reduce apply anymore, although this is a function name. Okay, the first argument, identity, was lost because the bound variable first does not appear in the body, second. Applying select second to arbitrary arguments, argument 1 and argument 2 returns the second argument. Now he's applying select second arg1, arg2. arg1, arg2, select second arg2, argument 2. We can show that select second applied to anything returns a version of identity. Oh, now comes this part. Oh, so that's the difference actually. Yeah, I see now. So select first. When you do select first, when you do select first, what did I do? Select first identity. Apply, select second identity. Let's do like this. I'll delete this. So, okay, we did it here actually. Select second. Okay, here. Select first identity, apply. Select SND identity, apply. SND. Why did I do this? Select first identity instead of first SND identity, apply. Let's see this. SND, I didn't need to do this. Yeah, this actually comes confusing now. So we have here SND identity, apply. SND identity. And what do we have? Select second. We expand here. And I expand. You see this? I expanded here the what am I doing here? It's weird. I'll delete this. So we have some SND apply. What did I do here? Let's try to do this again. So we have a select second identity, apply, which is the first, right? Second. And second, right? And then identity, and then apply. Well, we could close this too. Okay, apply. Okay, just to stay consistent with these things, let's close them also. Okay, so now here we substitute for the first, and then we stick with the second. Second identity, apply. Second identity, apply. Oh, this is wrong. Yeah, I see now. Now I see it. Okay. So here we had the second identity, apply. The second takes the argument of the first. Right? Look at this, the first. And it drops the apply. Apply cannot go here. You see, apply cannot go. Well, you could say actually apply goes here, drops the head, but there is no variable that it could take. So you're just being left with the identity like this. And you do not have to show the definition of the identity. But here we have identity goes inside of the first, right? But does not have any place. So we end up with SND, SND. You see, that's the difference. What is the difference? The difference is, apply. The difference is that select second gives out a version of the identity because we have the second and the second. It's just the same thing. So the second, lambda second is same as lambda whatever, right? So lambda second, you can even check that actually. If we go to code, if we go to code lambda, so I think we can even check that, like lambda x dot x, is it equal lambda second? No instance. We do have to apply it. Interesting. Can I just compare them? Okay, let's do lambda x dot x of 2 is that the same as lambda SND, SND of 2? True. So we see here it's the same. Lambda x dot x is equal to lambda SND, SND 2. It's true. So both give out true, right? Both will do the same thing. Right. That's why it says here in the book. We can show that select second applied to anything returns a version of identity. Okay, let's go on to standard arbitrary expression. Second becomes lambda xx. Yeah. Notice that select first applied to identity returns a version of select second. So this is important. He really tries out all the examples like shown so far. He applies them one to each other, you know, and see what kind of results you get. Now he's applying select first to the identity and returns a version of select second. It's almost confusing because select first being applied to identity takes the first argument. Select first identity, right? Select first identity, lambda first, lambda second, first identity. So identity should, select first. Yes, identity goes inside of first and you get the second identity. But there is nothing else to apply to. Second identity, second lambda x dot x. If second is replaced by first and x by second, oh, wow. Talking about conversions. What a fascinating. Yeah, I missed that the first time. Just a second. I'm not sure of the implications of this, but this is interesting. So he's saying that select first, right? Select first identity, right? Now, select first, right? So that's lambda first, lambda second, first. Will we keep the... Okay, we don't have to. So he's saying that select first applied to identity gives a version of select second. That was confusing at first. Like how does... But the point is because of the lambda, because of the alpha conversions. So if we substitute identity, right? Well, this is not hard now. Select first. And I think one thing that might be confusing is how does the select first work now? Because we are only giving it one argument, but select first is a thing that takes two arguments. So I think one part of me was like, shouldn't this like not work? But look, identity substitutes for the first. We drop the head. So we get the second, right? And identity. Now you might say, okay, how is now the second? How is this same as select second? Right? How is this same as select second? Wait, let's open up the identity. Lambda x dot x. What do we have? how does the select second looks like? Look at this. It's weird. Look at this. Okay, this is the select first. First, second, first. Select second is first, second, second. Right? Isn't this the same? Look at this. First, second, second. Second, XX. Like, what's the same? Well, here we have second and here we have first. But basically, if we need to change the whole thing so that it's, I don't know how would I show this, visually. But select second XX is same as second, first, lambda second, lambda second. Does this make sense? Because if we substitute, you see this is the same thing. Okay, you know why is the same thing? Because we could have like this. We could have a car. We could have a car and a person. This is also the same as this. There's no difference. And this is kind of a nice way to like think about, ooh, what does this mean? Because you see, we're sometimes very bound to what we're seeing, X. It's an X, but it's not an X. I mean, it is an X, but it can be also like a person. The computer does not care. This is for us, actually. But we do respect now the relation. Like, we couldn't put just car. It would not be the same. Yeah, okay. Max. Select first, second. All right. So select first applied to identity returns a version of select second. If second is replaced by first and X by second, then this becomes first, second, second. Yes, that's what we just did. All right. Making pairs. Wow. We're going to be making pairs now from two arguments. So we had select first, select second, and make pair. I wonder how you would make pair first. Well, now it's written, but I was thinking like some combination with the apply function, right? The apply, which had the FA. So the apply, which had takes an F, takes an A, and then applies F to A, right? Consider the function make pair. Finally, yeah. Make pair. So let's do make pair. Lambda first, lambda second, lambda func. Okay, I'm just gonna, I don't want to type so much func. I'll just do F and FST and SND. So let's do lambda FST, lambda SND. So this is a function that takes an FST, outputs another function that takes with a bound variable SND, and okay, and then outputs a third function. So we have three functions here. Lambda F, which does what? It applies a function to a first and second. Well, that's our make pair, actually. So make pair is a function that takes the first argument and the second argument, and then outputs a function that applies the function to first and the second. F and then F, well, F, FST, SND. Maybe we could use A and B. I'd like to use A and B actually. Well, I'll just type this all over. He wrote like this: func first, F, FSD, SND. Yeah, but the same could be said of, make pair. I like this actually. A, B, F, F, A, F, A, B. Well, you wouldn't have to write this. These are actually superfluous. What's the word? Because the function binding or function application goes from left to right. I think that's the right term, from left to right. Like you don't apply F to AB. You apply F to A. I mean, you do apply F to AB, but you apply F to A, and then it goes and applies to B, right? It's like this: F A. Well, how would you do it? F A, B, C, D, right? That's the function application. So you don't have to write it, right? Make pair A, B, F, F, A, B. And this is already in curried form, right? So this is actually already curried form. If you do make pair lambda A, well, interesting. Curried form, uncurried. What would be uncurried? Yeah, it would be just lambda ABF. Lambda ABF, FAB. Yeah. So we have now a make pair. What's a make pair? Well, make pair must be also some kind of combinator, right? Because it does not have any free variables which are not bound in the head, right? Everything what it does here, it's bound in the head. So it does some kind of combination. So interesting thing is, so far we've been actually, everything what we're doing so far were combinators. It's not explicitly said that in the book, but this is a combinator. So with bound variable first, and a body, this and this and this. So we have a bound variable A, or first, and this is the function body, which itself is another function with a bound head and a function body, which is another function head with another body, right? Which is another function with being applied to these guys, right? We have like 4 levels here. We have 4 levels. Interesting, right? I don't know how you could make it explicit these levels. You could, I guess you could do it like this. You could do it like this. So these are like 4 levels. So that's like the first function, the second, the third, and the fourth, actually. Well, I guess this is the third, but the fourth is the expression itself, right? So this function applies the argument func to argument first. This expression applies argument func to argument first. So the func is f, right? And the a is first and the b is second. So this expression, this function applies argument func to argument first. Argument func to argument first. This is thing, right? He's talking about the body itself. applies argument func to argument first to build a new function which may be applied to argument second. Right. So he's being that f is being applied to a to build a new function that it's being applied to b. Right? Because as we said, function takes a single argument. So we go step by step. So fa builds a thing. It's almost like saying, like plus 2 builds a function that has a 2 and adds what? Plus b. Maybe that's actually confusing. The function applies argument func to argument first to build a new function which may be applied to argument second, right? Why does it say which may be? Maybe that's just the English or Scottish, I'm not sure where is he from, way of saying this may be applied, may be applied, may be applied to an argument. It's like to be not so direct. Note that arguments first and second are used before argument func to build a function. Note that arguments first and second are used before argument func to build a function. Func, lambda func first, second. Note that arguments first and second are used before argument func to build a function. What does he mean by this? What does he mean by this? Arguments first and second are used before func. Maybe he means this actually. Yes. Now, if this function is applied to select first, okay, now we're going to apply make pair, right? Because we just have a name, the function name, and we have the function definition. So it's not like that we are going to now apply something here, right? We are going to apply this, the make pair, to another function. And we could try now to apply make pair to identity, to two identities. Could we make a pair of two identities? If this function is applied to select first, then argument, okay, so now we're going to apply make pair to select first. Then argument first is returned. And if it is applied to select second, then argument second is returned. For example, make pair identity apply. Let's do on our own. So we have make pair. We're going to apply that to what? To identity and then to apply. Okay, let's keep the parentheses. Make pair identity and apply. Apply, select first. I know because he just actually mentioned select first. Okay, he's going to do it here a bit later. So let's do it like this. Okay. Yeah, after a couple of days, this now makes a little more sense. I can feel more. Yeah. So we're going to substitute the function definition for the make pair, which is lambda A, lambda B, lambda F, FAB, and identity, right, and apply. So now we have what? Are we going to substitute identity for the head? Well, this is the thing, right? This is the thing I was confused about. Do you substitute identity now, here, or apply even? Because, no, this was a mistake on my part. As we said, function application, because we just expanded the make pair. Look at this. We can substitute this whole thing for make pair, right? But we can also substitute make pair for F. And then comes the question, would you go apply F and then identity F? No, F is being applied to identity. And then this whole thing is being applied to apply. So you cannot just now, okay, I'll do apply instead of A. So we have to do identity. And we're not going to expand on identity. We don't have to evaluate identity, right? So we're going to just substitute now identity inside of the make pair. And let's try this and let's see what we got. So we have lambda A. We will remove the lambda A head, right? So identity will substitute, we will remove the lambda A and substitute A. So that means we'll end up with lambda B. Lambda F and then F identity and B. So that means we are left with apply. Wow, isn't this awesome? I love this. Okay, look at this. Now we have a lambda B, lambda F, F identity B, apply. So now the next step would be to apply it. Let's do our substitutions. Apply, we're going to substitute lambda B and kick this guy. Okay, instead of this guy here, B, and we were going to remove the B head. So we're going to be left with a lambda F. And then this, and then F identity, and apply. Right? Makes sense? Makes wonderful sense. And now we have lambda F and F. So what do we do now? Identity apply. Well, let's remember what was F. F was func, right? But what was func? Lambda F, F is make pair. There's something else I learned actually yesterday. The eta conversion. Eta conversion says that lambda x dot x is same as, so lambda x dot x 2 is same as 2. So that means lambda f is same as identity apply. But wait a second, we have a make pair. Right. We called it make pair. And we defined it. So I guess we now have make pair identity apply. But how do we still make a pair, you might say? Right. All we did was just said FAB. No, all we did was say F, right? Remember, we have this and this. So we do have a pair now, but it's funny, like, what do you do now? Yeah, okay, let's see. Identity apply, right, right. Second func identity, second apply, right. Func identity apply, that's what we got. Func ff identity apply. Now if this function is applied to select first, oh, he's not, I see. Oh, interesting. Okay, he's now, what we got here, he's going to use that. And let's be consistent with what he's showing. Right, like this. Now he's saying, let's apply this to select first. Why? Let's see. Lambda f identity, apply. And he's going to apply this to select first. So what are we going to get now? Well, we could try, let's try. So we have lambda f. Oh. Again, the outer application. This might, but you might think like, what do I do now? Do I go apply? You see, you could almost make a mistake and do like this. The lambda f dot. There is no lambdas anymore, right? There's only one head here. Lambda f identity apply select first. So do we now, interesting, do we now do select first instead of this thing and remove the pair? Right, if we would do that, we remove the head. But no, we don't remove and substitute the F. But then what are we going to get? Yes, if we now apply F, right, we substitute here the F for the select first. We remove the head and we go and get select first, and then we get identity, apply. Check this out. We had select first, identity, apply, and of course we're going to have identity, select first, we're going to get identity. It's almost like a cheat. Wait. Now, if this function is applied to select first, right? Func, identity, apply, select first. Select first, identity, apply. Right. Select first kicks out the func, and instead of the func, we have select first, identity, apply. We expand. Oh, he expanded the select first. Did we do that too? We didn't actually, but yeah, it will be the same thing. Identity apply, and then identity goes into the first, and then second identity apply and identity, right? And if it is applied to select second, we get the apply. Yeah, that's clear from our pass. So select first would pick identity, select second would pick apply. But what happens with our pair? In general, applying make pair to arbitrary arguments, argument 1 and argument 2 gives make pair argument 1 and 2. But make pair, maybe he was trying to show us something else. Select first was picking something from 2. Select second was picking the second from 2. Make pair is creating a function, even though we might expect some kind of, magic happening here. But make pair is basically just showing F, identity apply, and that's it. That's the end. Interesting. How a make pair is F, 1, 2. It's almost like a very, subtle, simple way of saying. It's almost like you expect some kind of structure here, but it's just F. So a pair is a function being applied to two arguments. We're not picking one or the second. There is a very subtle thing here going on. Like, I guess you could say, why is this a pair? Where is this pair? Like, I want to see it. But again, we are doing function application. So function application that makes a pair would be a function identity apply. Make pair argument 1, argument 2, first, second, func, first, second. Argument 1, argument 2, second, func, argument 1, second, argument 2, func, argument 1, argument 2. Yes, thereafter applying this function to select first returns the first argument, argument 1. So he's showing us again here, okay, making a pair. And this pair, he was showing us, so this actually is same as make pair. So make pair being applied to select first. Gives out, interesting, applying this function to select first. You could almost say the thing, how is make pair being applied to select first gives out the first, right? Wouldn't you have to apply select first to make pair? How would that look like? Like, can we do select first to make pair? But I have to make pair what? This is not correct, right? Make pair what? I guess you could, but now we have to expand the whole thing. Do we remember lambda f? No, right? Lambda a. Lambda b. Now this is now tricky because make pair Yeah, I wonder what would happen because make pair has also A's and B's. AB is what? A. And make pair is lambda A, lambda B, lambda F, FAB. That's the select first and the make pair. So what would you do here? How is he applying select first to make pair? I get this, make pair argument 1 and 2. But applying this function to select first, func argument 1. Oh no, he's not. He's applying make pair. Oh, he's applying make pair to select first or second. Select first. Applying this function to select second. Func argument select second. Select second argument. Oh, he's substituting select second argument. I see. That's yeah. The thing is, you substitute the name for the definition inside. So I would have to like substitute select first, which is lambda A, lambda B, A, and make pair. And make pair is lambda B, make pair. So what do I get? I get just lambda B, make pair. Oh, interesting. I get what he's doing here. Maybe I'm still confused about these things. And applying this function to select second returns the second argument. Let's move on now. Free and bound variables. We are now going to consider how we ensure that arguments are substituted correctly for bound variables in function bodies. How we ensure that arguments are substituted correctly for bound variables in function bodies. If all the bound variables for functions in an expression have distinct names, then there is no problem. He's talking about free and bound variables. Let's take an example. A lambda f, lambda xx, lambda s, ss. So this is a function with this body. The body itself has another function and another function, which are applications to this function and these arguments, which are another function with the head and with the body, and with the argument application of SS. There are three functions, I guess. One, 2, and 3. The first has bound variable f. The second has bound variable x. Oh, he's talking about this one. He's counting the lambdas. Okay, you count the lambdas. I was counting this f actually, because f is being applied to this. There are three functions. The first has bound variable f, the second has bound variable x, and the third has bound variable s. Thus, lambda f, lambda s, lambda xx. Interesting. Lambda x, lambda x, lambda x. It is possible, however, for bound variables in different functions to have the same name. Consider lambda f, 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 s, s, s. Oh, yeah, what would you do here? You could substitute the lambda x dot x with lambda f dot f. This should give the same result as the previous expression. Here the bound variable f should be replaced by lambda s, s, s. Now you could replace this thing with this thing. Note that we should replace the first f in f, but not the f in the body of ff. This is a new function with a new bound variable which just happens to have the same name as the previous bound variable. To clarify this, we need to be more specific about how bound variables relate to variables in function bodies for an arbitrary function lambda name and body. The bound variable name may correspond to occurrences of name in body and nowhere else. Formally, the scope of the bound variable name is body. Yeah, this is kind of more clear, but he's now making more explanations here. What's going on? Formally, the scope of the bound variable name is body. Yeah. Lambda f, lambda s, f, s, s. The bound variable f is in scope in s, f, s, s. Because all of them are declared in the head, right? It's like almost like if you had a y here or I don't know, bloop, which is not declared in the head. That would be unbound or free. And lambda x, lambda g, lambda a, f, g, a, g, g, g. The leftmost bound variable f is in scope, but he's talking about something else here. I guess he's talking about scope. Scope in the sense the leftmost f is in scope where? Here. Yeah, like what's the scope of this f, of this bound? It's all the way here and nowhere else. Oh, it's here. It's not here. Yes, because this is at the same level though, scope level. Look at it. Yeah, we have the parentheses here, right? But let's say we don't have them. We have lambda f and lambda g here is on the same level. Got it. You see, it's on the same level. So the scope of this f stops here. And also this g is not the same as this g. These are two different g's. This is not the OG. Both of them are the OG. And nowhere, that's a joke. And nowhere else, similarly, the right mode bound variable g is in scope in gg and nowhere else, right? Note that we have said may correspond. This is because the reuse of name may alter a bound's variable scope, as we will see. Now we can introduce the idea of a variable being bound or free in an expression. A variable is said to be bound to occurrences in the body of a function from which it is the bound variable provided no other functions within the body introduce the same bound variable. Yeah, I don't know what you just said. I kind of get it, but it's just we can introduce the idea of a variable being bound or free in an expression. Okay, now we're going to introduce this new idea that I want to show you after we kind of shown the scopes here. So if it's on the same level, it's not. You could have a lambda f and some other lambda. A variable is said to be bound to occurrences in the body, right, of a function for which it is bound, provided no other function within the body introduce the same bound. Otherwise, it's said to be free. Okay. So it's like we have the lambda f. What if we had like lambda... Yeah, it's clear. It's just I'm trying to really see it more clear. This thing provided no other function within the body introduced the same bound. So it's at least saying like, let's say you have g, lambda a, and then here f, g, a. But maybe you have like lambda, I don't know, lambda c, and it has a g also. I think that would be a problem then. Like, would that be even possible? Let's say you have two G's inside, but one is bound with a different head. I think he's saying that. Otherwise said to be free, thus in the expression, let's look at a basic case. Thus in the expression lambda x dot x, right? The variable x is bound, but in the expression x, the variable x is free. Oh, he's comparing now the two most actually basic cases. Nice, nice. So this is free, right? Like, okay, lambda x. What? Lambda x, right? This is bound. That's why we can substitute for 2. It's bound in the head. It's not free, right? But if we just write this is free because it's not bound in any head. So that's why we don't have a value. Variable not in scope. It's not in scope. And even if we give it something like 2. Variable not in scope. So these are actually the most basic in lambda x. I guess another way how you can show it, if you say lambda x and then y, would this work? It would not work because y is free and it has a bound x. Variable not in scope y, you see? Same as in here, lambda x, xy. Variable not in scope. Perhaps use x. Perhaps. Okay. In general, for a function, he's showing here also. The variable x is free in, okay, lambda f lambda x dot x. Really? How is this free? It's like tricky thing. Because we have a lambda x dot x. This is the identity function. How is this free? The variable x is free in, the variable f is bound. Yeah, but in the expression lambda x dot x, the variable f is free. The variable f is free.